Hi everyone, welcome for joining us in this webinar session. The session will start in 5 minutes. We'll just wait for the other participants to join in as well. So kindly stay tuned. In 5 minutes, we'll be getting underway with our session. Okay. If I'm audible, and visible to all of you, kindly give a thumbs up so that I can go ahead with the session. Okay. Thank you so much. So welcome everyone once again to another webinar of Researcher on Web. Before we get underway with our webinar, there's a few guidelines and a few things I need to tell you. Firstly, all participants have been kept on mute without the option to unmute yourself. This is done so that any background noise on your part does not interfere with the speaker. If you have any difficulty with the audio, you can't hear the audio of the meeting, or you can't connect to the meeting, then you can either go to the YouTube link that's provided in the WhatsApp group, or you can contact me or Shubho, the admins of the WhatsApp group, and we'll resolve your issue at the earliest. So that being said, so let's start with the session. Now, before we start, I just want to say a few things. We have been doing this research on web webinars for a while now, and we interact with a lot of researchers. And a thing that we have noticed among a lot of researchers is that society somewhere always asks the question, what can PhD ever do for you? Like a student, a PhD scholar would go and answer that they do it for the love of science or that they contribute to society, but there's always this stigma that you should do a job or you should go ahead and do a business. So today we have with us someone who's answering these very questions because her research work done during her PhD is making her an entrepreneur. So today we have with us Ms. Ekashmi Rathore from the Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, where she has devised during her PhD itself a innovative device and mechanism that removes impurities and harmful metals from water from everywhere, from a lake to even a teacup. So, and as you will see during the course of the webinar, she explains it, why it's great for a business or for a product, because it ticks all the boxes you need for an innovative startup product. It's innovative, it's highly effective, it's better than anything in the market, and it solves a major issue in society, that is water purification. So without further ado, I'd like to hand over the stage to Ekashmi. I'll let her break the glass ceiling and explain us about the amazing work that she has done. Over to you, Ekashmi.
Hello, science enthusiasts. Thanks for joining my webinar on the platform Researcher on Web. So today I will share how my research is helping the society to purify water bodies contaminated with toxic heavy metal ions. And I'll share how I got inspired from nature's insect-eating Venus flytrap and design materials and prototypes. I designed this tea bag which you can put in the water bodies, and it can soak up all the heavy metal ions. So stay tuned till the end to watch out all my products. So I am Ekashmi Rathore and I am from Rawatbhata, Rajasthan. I have done my schooling from Rawatbhata, Rajasthan under Department of Atomic Energy, and which hosts the India's nuclear power plants. So this was one of the reason which made me do my PhD in chemistry. So I did my Bachelor's of Science in Chemistry honors from University of Delhi in 2014. And with my persistent desire for the science, it landed me an opportunity to work under an eminent scientist. And I even got best thesis for my master's project. So with these amazing facilities at JNCSR and less number of students, I decided to pursue my PhD at JNCSR itself. And in upcoming years, I aspire to be a woman entrepreneur by bringing the technology from lab to market. So my PhD thesis is titled as Metal Chalcogenides, Chalcophosphates, and Halides for Energy Conversion and Environmental Remediation. So during my PhD, as a solid state chemist, I have designed and synthesized materials for the application in energy conversion and water purification. This water purification part is very close to my heart, and it all started with the news of that Maggi noodles got banned back in 2015. And I was very sad, like we enjoy eating Maggi so much, and how it got banned. So the reason why it was that Maggi started having lead, and lead is known to have toxicity, and there were instant bans in Maggi in various states like Gujarat, Tamil Nadu, J&K, Uttarakhand, Telangana, etc. And the reports came that it had 17.2 parts per million level of lead contamination, while the allowable range is just 0.01 and 2.5 ppm. So the scientist brain in me started thinking about what's happening. I mean, how is lead going into the Maggie? So is it the water that contains the lead? So I realized that this was my time to be the Wonder Woman in the chemistry lab. So do you know how much water is there on the earth? So Earth is very special planet because it has so much of water. It's in the ground, it's in the big oceans, and it's even in the atmosphere. Even you, me, and all the life forms are made up of water. So it consists of 71% water at the surface, and out of that 71%, 96.5% is in our oceans, and it's mostly has salts like sodium chloride, potassium chloride, magnesium chloride, etc. And just this 3.5% of this water is fresh water. And out of this, 68% is trapped in the glaciers. Now, the one third of this fresh water is basically the groundwater. And the rest lies in the water bodies like lakes, rivers, and streams. And a very small amount is in the atmosphere. So imagine that the water surface area of earth, and if you check the put all the water bodies together, it will constitute this small 860 miles wide, and that's a lot of water. But the thing is, the population is 7.9 billion people, and there is just 3.5% fresh water, and that too is getting polluted. And what exactly are we doing to our water bodies? So much pollution is there in water. So now let's have a look at the types of pollutants present in the water bodies. So the first one is the suspended solids. So these suspended solids can be removed just by the normal filtration processes, or by using sand or clay. But the second is the biodegradable organics. So these are basically the proteins, carbohydrates, and fats. The other is the pathogens. So pathogens basically are invisible to our eyes, and they are harmful to our bodies. And the other is nutrients, which is basically nitrogen, phosphorus, carbon, and these comes from the fertilizers which we use in agriculture. So if you use excess of fertilizer, and when the rain comes, it gets washed away into the water bodies, and these are toxic in nature. The another is priority pollutants. So this comprises of highly toxic chemicals like arsenic, and they have toxic effects on the body. The other is refractive organics, and it comes from pesticides, phenols, and surfactants which we use on our daily basis. The most dangerous thing is like these heavy metal ions. So heavy metal ions are basically dissolved in the water. Okay, so it's very difficult to remove the dissolved impurities. And the other thing, we cannot see it from our naked eyes, and they're highly toxic in nature. So let's have a look what are the harmful effects. So these are the major heavy metal ions, which is mercury, copper, lead, cadmium, arsenic, and chromium. So it has adverse effect on human health, like it causes headache, fatigue, respiratory issues, heart diseases, stomach diseases, nausea, skin irritation, and you do not see these immediate effects. It comes over the longer period of time. I mean, people suffer from intellectual disability, and in children also, it leads to the slow growth. And it is known to have adverse effect on plants also. Like there is inhibition in the growth of the plant. There is reduction in the photosynthesis, and there is death due to the reactive oxygen species production. And plants take less amount of water. So immediately it has lots of effect on plants also, and it has effect on aquatic organisms also. Like there are chances of possible infections. The fishes will have a decreased egg production. They will suffer from respiratory issues, and it will be very difficult for them to get oxygen from the water. So now let's have a look how it basically hinders these at cellular level. So these plants take these heavy metal ions from the soil and the roots, and it goes up and it's get deposited at various places of the cells. So here this reactive, this is a plant cell. So here these heavy metal ions will go inside the cell and it will inhibit the enzyme. How they will inhibit? These enzymes have like metal ions, other useful metal ions like zinc, Zn2 plus. And these heavy metal ions, if they have the similar charges, will inhibit the enzyme. And if the enzyme is inhibited, then most of the cell activities will be disturbed. So let's say there will be damage of mitochondria and chloroplast, then there will be DNA damage. The cell will not be able to do transcription or translation. There will no be production of protein, and as a result there will be disruption in the cell membrane. So it's toxic in plants. Now coming to the humans, like it can lead to the formation of reactive oxygen species, and it will lead to the transformation of the cell and lead to cancer. And then there are this is double stranded DNA, and it will get converted into single stranded DNA, and there will be high level of damage, and which will lead to the cell death called as apoptosis. Now let's have a look how these heavy metal ions come into the water bodies. So the most major part comes from the mining industries, then agriculture, wastewater, and then urban discharges. So these are the anthropogenic sources of heavy metal ions. So industries like distillery, acid mine drainage, tanneries, batteries, or smelting, or other electroplating industries discharge these heavy metal ions to the water. Now these sources can be categorized into five forms, like the natural, which comes from the rock or the volcanic eruptions. Then there are agriculture waste, which is due to the excessive use of the fertilizers or the sewage sludge. Then there are industrial discharges coming from the chemical or the mining industry. Then there are domestic discharges like electronic waste or the used batteries. With the improvement of technology, with the being digitalized, we are using more and more of batteries, and this is very harmful for our water bodies. And then there are dumping which is happening, the landfills. Then there are traffic emissions. So all of these causes introduction of these heavy metal ions into the water bodies. So now let's see this bar plot where you can see that or the various industries like engineering, paper mill, fine chemicals, or dyes, paint, all of these are discharging heavy metal ions like chromium, cadmium, nickel, zinc, copper, and lead. So it's very dangerous, and you see that it's the concentration in parts per million level, and which is very high. And the drinking water limits are usually in parts per billion level. So we see here that lots of toxicity is coming into our water bodies. So now let's have a look what are the current technology available in the markets. So industries use resins and mesoporous silicates or zeolites, activated carbon, or clay. Most of these material suffer from various issues like pH stability. Now you imagine these heavy metal ions are going into the water, and water will have different types of pH then, and it will be difficult for these material to act on that particular pH because they are not stable. The other issue, like for the making a low cost like technique, is that the material should have more capacity. Let's say you use cartridges, and you need to replace these cartridges which we use in purifiers every year. So we need to make materials which have high capacity, and it reduces the cost also. The main challenge right now is to remove the heavy metal ions in parts per billion level. And it means that let's say there are 10,000 molecules, and only 10 are heavy metal ions. So the material should be able to capture only those 10 atoms of heavy metal ions. So that's a big challenge, and the material should have high selectivity in capturing only heavy metal ions. The other thing is that the material should have strong binding affinity towards these heavy metal ions, so which will increase reduce the time required to capture these heavy metal ion. So I took the inspiration from nature's Venus flytrap, and what excited me was like this Venus flytrap captures the insect. So I thought, like, can I capture the similar way the heavy metal ions? So I took the help of layered materials. So in layered materials, two layers are there, and there we can explore the exploitation of the layer space can be done. So what happens is like there will be increase of the surface area above and below the layers. So it gets increases the material adsorption sites. So it will increase the capacity. The another thing was like I took the basic chemistry concept of hard soft acid base theory. So I thought that these heavy metal ions are soft acids, and can I design soft Lewis based framework materials? So there will be immediate interaction, and there will be strong interaction between them, and it will be able to remove efficiently these heavy metal ions. So now coming to the talk. So so I took the inspiration, and I used layered materials for the purification. So these are the materials which I have designed for the capture of lead, mercury, chromium. And the first one is layered metal chalcophosphate. The other is graphene oxide and tin sulfide composite. The other is cobalt aluminium layer double hydroxides. So the speciality of all of this material is that it can capture the heavy metal ions from parts per billion level. And here in the first I will cover this lead. So lead is highly toxic in nature, and it's known to cause lead poisoning, and which leads to the slow death. So with the exposure of lead, it leads to the damage of the nervous system. Children suffer from slow growth and development. There are learning and behavior problems. So these effects you will not see immediately, but let's say after 10 years, 20 years, you will definitely see those effects. And here we see that tons of lead is getting discharged into wastewater or in the sea, and the lead pollution is all over the world. And even in India, various cities are at alarming risk. So I came up with a solution. I designed layered metal sulfide, and so it called as MnPS3. And these are the P2S6 units sandwiched by the Mn2 plus ions, and this layer spacing is 6.45. So to improve the efficiency of this material, I intercalated potassium so that this layer spacing increases, and it will help to capture lead efficiently. So now how do we make this compound in our laboratory? So we take the stoichiometry amounts of manganese, phosphorus or sulfur powder, and then we grind it in a pestle and mortar. Then we seal tube the reaction. So we conduct this reaction in vacuum. So the vacuum pressure will be around 10 to the power of minus 4 torrs, and we keep this tube which we have sealed for 750 degrees Celsius for 7 days, and it gives rise to beautiful green color compound. And when we do the treatment with potassium chloride, it changes its colors to light green. And for the conduction of all the lead sorption study, I prepared artificial solutions using lead nitrate. And here you can see that there is a color change. And this is a powder X-ray diffraction pattern where the 001 peak correspond to the layered peak, and which tells us about this layer spacing. So when I intercalated potassium, the layer spacing increased and it shifted to the left. And when I used treated it with lead nitrate solution, it shifted to the right part. So it tells us that something is happening and ion exchange is happening. So this is a classic characterization technique which we use in laboratories to find out whether lead is going into the system or not. So then I conducted energy dispersive X-ray analysis, and it tells us that what kinds of elements are present in the compound. So these are the scanning electron microscopy images, And here you can see that this potassium is being replaced by the lead ions, and it tells us that there is complete removal of potassium ions and this option of lead takes place. So here in the we see the color change here, and the band gaps tells us that there are large covalent interaction between lead and sulfur with respect to potassium and sulfur, which destabilizes the valence band, and there is reduction in the band gap to 2.45. Now, let's have a look how this binding happens and what is the mechanism behind the lead sorption. So here this is a MnPH3 structure, and this green one is potassium. So when we introduce excess positive charge in the system, this Mn2 plus goes out, and to maintain the charge neutrality. Now when we treat our samples with lead nitrate, what happens is this lead goes to the vacancy sites created by manganese. So this is the mechanism, and we have found it out using IR spectroscopy and Raman spectroscopy. So till now I discussed about the qualitative analysis. Now let's see how can we do the quantitative analysis. So I've used the physical chemistry tools to determine maximum sorption capacity, kinetics, selectivity, and detection limit. So how do we carry out this study? So we use like 10 milligram of our sample, and we take 10 ml of the artificially prepared solutions in the range of 400 to zero point 0.2 ppm. So with the help of tube shaker, we rotate the samples, and for 24 hours, then we remove the material and take the liquid and do the analyze the samples for the concentration. Let's see whether the concentration decreased or not. So for this we use inductively coupled absorption spectrometry. So what happens in this technique is like the liquid samples will be ion sprayed with the use of plasma, and it will these elements will separate out, and with the help of spectroscopic lamp, each element will show peaks at different wavelengths. So it will help us to detect those heavy metal ions which are present. And for this ICP-OS helps us for the detection in parts per million level. And for the parts per billion level, we have used ICP machine attached with a mass spectrometer. So here you can see that the initial concentration are ranging from 400 to zero point 0.3, and my final solutions have decreased. See, such a low concentration I have got for the lead. So we found out that there is more than 99% removal of the lead happening in the our system. And now we wanted to calculate like what will be the capacity of this material, and like how much lead it can capture. So we took different solutions and different concentration solutions, and used our material to capture. And with the help of this capacity formula, where C naught is the initial concentration, it is the final concentration, and V is the volume, which is 10 ml, and M is the 10 milligrams of sample which we have used. So we calculate these values, and we found out that the capacity is 393.5 milligram per gram. So what it means that 1 gram of the material can capture 393.5 milligrams of lead. Now the another character, like to understand whether the material is highly efficient or not, the other parameter is distribution coefficient. So distribution coefficient should be in the range of 10 power 3 to 10 power 5, and it can be calculated by using this formula. So we have obtained very high distribution coefficient values, which tells us that our material is highly efficient in nature. Then we wanted to understand how fast this material can capture lead. So here you can see that it can capture lead 100% in 24 hours, and the equilibrium reaches in just 8 hours. And we saw that 100% removal of the lead. So this happens due to the chemisorption with the adsorption mechanism via metal sulfur bonding. So now let's have a look what happens in different pH solutions. So this material is highly stable as indicated from the powder X-ray diffraction patterns, like it's stable from 2 to 12 pH range. And we were able to remove more than 99% of lead. And here the values can tell you that it's of the order of 10 power 5, which means that it's good in nature. So now the mineral water contains potassium, calcium, magnesium, and sodium. All of them are like 1 plus monovalent or divalent. So we wanted to check whether it can remove lead even from presence of these metal ions. So we carried out competitive ion exchange study, and here you can see that we took a similar concentration range of these metal ions, and surprisingly we found out that only lead was getting removed. So here you see that 97.5% of lead was getting removed. So this experiment showed us that it's highly selective in towards lead capture, and this selectivity arises from the soft Lewis based framework of KMPS1 and soft Lewis acid lead. Now coming to the low capture study. So this low capture study is like a very unique or like a very interesting part of my research. So the drinking water limit for lead is like 15 ppb. So the materials which I have designed were able to capture from 1 parts per billion level. So I got really excited, like can I do the real sample collection and do some study. So from the nearby lake near to my campus, I collected some samples in one morning, and then I analyzed. And surprisingly, I found out that there was 68 ppb of lead in that lake. And the samples I collected, I treated with my material, and I was able to remove 99% of lead from the water bodies. So now coming to the how efficiently is a comparison with other solvents, it performs well and it works in broad pH range. So the next part I will talk about is capture of mercury. So mercury is known to be toxic in nature, and we have seen that it has caused Minamata disease. And so how mercury travels in the food chains, so and it leads to the biomagnification of mercury, and it has toxic effects like it harms the brain, kidney, heart, birth defects, and you can even see the skin diseases. The thing about mercury is like the tolerance limit for drinking water is 2 parts per billion level. So how can we remove mercury from such a low concentration? So I came up with a solution, and I designed a composite of graphene oxide and tin sulfide material. So why graphene oxide I used? The motivation was that it has high surface area. But the problem with graphene oxide is that it lacks selectivity for mercury. So to introduce this selectivity, I added tin sulfide material. So it implemented selectivity in the material. So here you can see that there will these purple ones are mercury, and here you can see that they are binding and playing a synergistic role, that is high surface area with selectivity. So I synthesized this material in laboratory by taking the graphene oxide dispersion, then using the precursor like tin chloride and thiourea, and it was all dissolved in water. And then we transferred this solution into autoclaves. So autoclaves are like these tiny pressure cookers which we use in lab. So we did the thermal treatment at around 160 degrees Celsius for 16 hours, and we found out that liquid phase and solid phase separated, and we filtered this and we dried it, and it led to the formation of the desired compound graphene oxide and SNS2. So here in the powder X-ray diffraction pattern, you can see that this is the spectra for graphene oxide, then this is for SNS2. So when you mix these two by using this method, so we see that the graphene oxide starts having the peaks of SNS2. So we then did analyze this sample, and we wanted to look the morphology. So we went to use these transmission electron microscopy, and here you can see they visualize the structures at just 10 nanometer. And here this is the sheets, graphene oxide sheets, and these dots are coming from the SNS2. And with the energy dispersive diagram, we could see that mercury is there in the sample. And we found out that there is direct metal ion absorption from this experiment. So now we wanted to know like how mixing these two is helping the capacity. to increase. So if you can see that graphene oxide and SNS2, the red compound, is outperforming the other two, like only graphene oxide and SNS2, and there is an increase in the capacity of the material. So that's how we introduce selectivity in a material and how we design new materials. So we did a competitive ion study with other metal ions like sodium, potassium, cesium, or all those monovalent or divalent, and we found out that it's highly selective in nature. And here you can see that I wanted to understand whether is it particularly binding to only mercury heavy metal ion or other heavy metal ions also. So here I did with other heavy metal ions, and I found out that it's highly selective towards the mercury ions, and this is due to the soft Lewis based framework of SNS2 grafts on graphene oxide and the soft Lewis acid mercury ions. So now coming to the pH study, we found out that the material is stable in 0.5 to 11 pH, and more than 90% of this mercury could be captured. So we then performed the kinetic studies, and we found out that it reaches equilibrium within 2 hours, and 100% mercury removal could be obtained within 3.5 hours. So with these amazing properties, I wanted to study whether it can be captured for low parts per billion level. So the drinking water limit is 2 parts per billion level, and my material which I designed could capture even from zero point 0.3 parts per billion level. And here you can see that it removed 99.9% of mercury. So coming to the prototype tea bag, so I got excited, like, can I have a practical application? How can I implement this in real life? So what I did was, like, I recently that time I started drinking green tea, and I came up with like, okay, let's take this tea bag, put my material in it, and assume that my this beaker is a water body, or whatever you call pond or lake. So, and what surprisingly I found out that it was able to capture these heavy metal ions, and it could remove 100% mercury in just a few minutes. So that's what I got excited, like, the research can have a practical application too. So now coming to the chromium part. So chromium is also toxic in nature. So till now I have discussed like positively charged ions like 2 plus lead and mercury. So now how can we capture anionic species? So chromium exists in oxyanion species like dichromate and chromate, and the tolerance limit at 50 ppb. So this chromium is known to have toxic effects, like it's carcinogen or in mutagen in the biological system, and it gets released into the water bodies from the industries like chrome plating, dye industries, or leather tanning industry. Even Van Gogh's painting use the colors made from lead chromates. And here you can see that tons of research keeps coming, that chromium is coming into this water body or that water body. So this news articles give me a chance, like, okay, I can start working on chromium also, and it is very important to remove it. So I came up with another solution, and I designed cobalt aluminium layer double hydroxide. So here these layers are positively charged layers of metal hydroxides, and it facilitates the surface adsorption. And these anions basically comprises of carbonate layer. So this carbonate is non-toxic in nature and can be exchanged with the anionic species like dichromate or chromate. So in the lab, we synthesized by using this our small pressure cooker, and we used aluminium nitrate and cobalt nitrates for the synthesis, and we formed this pink color powder. So I got wanted to look this at micrometer scale. So I did scanning electron microscopy images, and here you can see that this material has beautiful structure, and this beautiful structure looks like coral reefs, which we see when we are doing scuba diving or we are going some water bodies. So, and from this experiment, I figured out that before and after adsorption, there is no morphology change, and here you cannot see the chromium peaks, and with the chromium adsorption we saw the peaks of chromium coming. So it tells us that there is removal of carbonate ions, and there is adsorption of chromium taking place. So the another interesting part was, like, I visualized my powder samples at the nanometer scale, and with the help of transmission electron microscopy, and what we found that these layers are hollow from insides. So this hollow nature gives rise to high surface area, and if there is high surface area, then there is more probability of these heavy metal ions getting captured. And from the colored mapping images, we figured out that chromium is evenly adsorbed over the surface of LDH. So I carried out the similar kinetics, pH, and competitive ion studies, and we found out that sorption is completed within a minute, and it can remove more than 90% of this chromium ions effectively. And even in the presence of other anions like chloride, fluoride, bromide, or nitrates, this shows that it's selective in nature. So with these amazing properties, we checked the low parts per billion removal. So our material could capture even from 4.5 ppb level, and while the drinking water limit given by the USA EPA government is 100 parts per billion only. So we decided to compare our results with other materials, and we found out that our material is the best one. So with this, like, I thought that, okay, let's make a prototype of this and how it will work. So the thing is, like, if you want to make a market size product, it should be low in cost. And so my material, I try to mix it with inexpensive sand, because it will help us to safeguard the continuous flow of water, so the column will not get clogged here. So the sand basically acts as a support system. So also it helps us in providing more surface area, so that more and more heavy metal ions can be captured. So this is on the left side, you can see the sand column, and when you pour the yellow colored chromium solution, it doesn't remove. And so you can see that it's such a low removal, or it's not at all removing. So here, so when I mixed just 2 grams of my material with 18 grams of sand, and I constructed this column, we found out this yellow color is changing into white. So this colorless solution, so it's a clear indication that chromium is getting removed. So we found out that from our column studies, that we could able to remove 99% of chromium, and with a very high distribution coefficient. So in conclusion, like, I have tried to remove heavy metals like lead, mercury, and chromium. All of these are working in broad pH range with very high capacities and strong binding affinities for various heavy metal ions, and it has high selectivity towards the other metal ions present in the water. And the interesting part, or the most novelty of my work, lies in this, that my materials could able to remove from such a low concentration of contamination. So so if you are excited to do this research, so here are some references which I have attached. So the first one will help you to study, like, what kind of materials can be good ion exchangers. So this review will help you to understand the previous technologies and what kind of materials scientists have been designing. So this is a recent book which will help you to understand the new upcoming techniques or trends for the removal of heavy metal ions from the industrial waste. And then for the experimental section, or how I have conducted my experimental studies, everything is written clearly, and you can refer this article. And for any other queries, or you can reach me out at LinkedIn. I am as Ekashmi Rathore, and I would like to acknowledge my professor Kanishka Viswas for giving me an opportunity to start a new field, like not being restricted by living in JNCSR. So I mean, like, I could able to conduct my experiment, go to another institute and do all the experiments. So this was he has been a supporting for me. And I would like to thank Professor CNR Rao for constantly like being inspiring us to conduct research. And the other thing, he used to call me her radioactive girl. And this was like some like a granddaughter touch. And you can also check out my talk on YouTube. So this talk I gave in Falling Balls lab in 2017, where I represented India, and I represented my research at an international platform. So thank you for your attention, and I would like to answer your questions.
Thank you, Ekashmi. Thank you for the great session. So that was our only chance to go to Goa and try scuba diving during this pandemic. Anyway, thank you, Ekashmi. So the room is now open for questions. So any person can ask any question related to the research topic, which Ekashmi just spoke about, by the raise hand option in Zoom. So what you have to do is you have to raise hand. There will be an option raise hand on the participants tab. If you're opening from phone or if you're opening from your laptop, you can go on the right hand side. There will be three dots and you can click on the raise hand option, or below the reactions also you can have a raise hand option. So you can just raise your hand and ask your question. So we have got the first question from Shubham. So Shubham, I'm giving you the permission to unmute. Kindly ask your question.
Yes, am I audible?
Yeah,
Yes,
Shubham,
you're
you're
audible.
audible. Yeah.
So you have told that the introduction of the ion absorption is for lead and mercury is the metal sulfide interaction. So what is the case for chromate ion? Means
Okay.
what type of interaction in between lead hydroxide and chromate for absorption?
It's similar to hydrogen bonding. So there are interaction between like you say Cr2O7 2 minus. So it has 2 minus charge, and the material is like positively charged. So there is a electrostatic force of attraction between them. Did you get it?
Shubham, you can unmute yourself and you can.
Yes. Thank you.
Thank you, Shubham. So we have got one more question. We have okay. If you have any problem in speaking, or if you are in a situation where you cannot ask your question, you can also type the question in the chat option. I will ask the question on your behalf. So we have got another question from Rajnandini. She's asking, how do you deploy this in a big water body like a big lake?
Okay. So we are into the formation of prototype. Let's say uh, if we block the point source, like from where the contamination is coming, let's say the industry is releasing their effluents into the water bodies. So we can make a similar sorts of bag, and that can the pipe from where it is coming can be blocked. I mean, like, it will capture immediately from the point of source. But now what about the what is there in the lake currently? So we can do the treatment with our material the same way. Let's say we mix our material with sand, or like some sort of bags we need to create, which we can directly put it in the water bodies, and it will. So the boat. So if you want to remove like from the entire lake, you can put that bag to the motorboat, and the motorboat can roam here and there, and it can capture. So this is an idea like I would like to do, proceed further.
Okay, so the person cannot interact, but I think that will be a great activity for her or for him as well. So yeah. So the next question is from Shobana. So I'm giving you the permission to unmute. Sana, you can ask your question.
Hello, Ekashmi. Can you hear me?
Yes, I can hear you, Sana.
Hello, can you?
Yeah, Sana, you are audible.
Hi, Ekashmi. Very nice talk and very nice results and very well explained as well. Thank you for the talk. My question is, how do you dispose of these adsorbed materials? I was just wondering, maybe I missed it during your talk, or maybe
uh,
how do you dispose of these materials after they are adsorbed? I mean, you adsorb them on your materials, and I mean, after you have these all toxic materials, how do you dispose them off? I mean, yeah, this
Okay.
was the question.
So whatever the materials, let's say I have used lead. Okay. So if I'm using it a sulfur material, base sulfur material, so it will be behave like an ore. So you have an ore of lead sulfide like galena is which is there already there present in the earth. So whenever you need, you can take it out for the other usages. So it will be like in a ore.
Okay.
And some of the materials like cobalt is the other two materials are like reversible in nature. So when you do a treatment with let's say for the ldh case, if you do the treatment with potassium carbonate, so it will do the reverse reaction. So all of the dichromate which was there, it will get removed and the carbonate will be replenished. So this column can be used again and again.
Okay, great. Thank you.
Welcome.
Thank you, Sana. So the next question is from Aditi. And Aditi, can you ask the question if I give you the permission to unmute? I have given you the permission to unmute. Can you ask the question on yourself? Or do I need to? Okay. So like, yeah, it seems that she's having some network issue. So I'm going to ask the question on her behalf. So were you able to separate the heavy metal ions from the materials you made so that you can reuse the materials?
Reuse the materials. So, so the same question with Sahana asked, and I answered like if it comes in the form of ore, it will be an ore, and it can be used. So we all know that lead is present in the form of galena ores, so those you can use it. But I mean, like you need to remove it. So let's say I talked about the reversibility studies, and for from there you can remove the dichromates ions, so you can use them back.
Okay. Okay, Kashmir. So the next question is from Anirban Roy. Is asking, is there any side effect to this, like harming the aquatic life?
So we need to carry out the toxicity studies, like what are these heavy metal, I mean, like the material is doing with the cells. So we need to do. So our main goal was like first to capture these heavy metal ions. So we are in the process of doing this toxicity studies.
Okay. I guess that question has been answered. Okay, so one more question from Rajnandani herself. So, is there any way to make it? Okay, so it's not. I'm not asking this. Is there any way to make it quick and effective so that the cleaning could be so fast that we attach it to a bottle cap and drink directly?
So as I mentioned, like we haven't done the toxicity study for these materials, and I believe that they are non-toxic. That you can make like a bottle, and there are like some. Have you used that water which we use for like basic alkaline water? How do we make it? Like we put some fruits inside, and the water,
Yeah, yeah.
the juice of the fruits get discharged into water. So similar type we can definitely take and remove it. But I'm not sure about the toxicity part yet. So we are in the process of doing that.
So I think we need a super special water bottle for that. So okay. So any more questions? If you have any further questions, you can ask it now. Room is open for questions. If you have any problem in asking the question yourself, you can also put it in the chat box. It's also getting streamed YouTube live, so I think yeah. Um, if there is no further question, I think okay. So yeah. So Ekashmi, any concluding remark on the entire session and on how your research life was?
Okay. So firstly, I would like you, like the researcher on web, and you and Subupriyo and Aniruddha for giving me an opportunity to communicate the research in a simpler way. And I thank all the participants for coming for my talk. And I believe if we are able to do more and more of science communication and tell people we are doing great science, and there will be chances of increasing funding also. Even people will not say that to you, I mean, the people who are doing PhD, that you are taking taxpayers' money and you are not doing anything. So what's happening currently, I mean, like in most of the places in research institute, people are after publishing the papers, and they are running behind the publishing, and like because they will get promotion and that and all. But what right now needs to be done is to address the climate issues. We need to address the energy and environment issues. It doesn't make sense that you are making a you are exploiting the research sources, and you are not doing justice to it. So I think these PhD students should have a setup this sort of mindset, they should come up with a application, or like they come up with some startup idea, and that's how we can help to boost our India's economy and create more and more jobs. So that's what I would like to say.
Okay. So thank you, Ekashmi, for such a great webinar session. This is exactly what we look for in our platform, Researcher on Web, where a researcher can have an impact on the society by his or her research. If you think your research is impactful, or even if you think that it's fundamental but very less known by the people around you, you can be a part of our platform. All you need to do is to simply go to our website and apply, and you can be a part of the live interaction webinar session. That is, you can talk to the audience directly, as Ekashmi did today. You can also be a part of our future podcast sessions where you don't have to show your face and you can talk endlessly about your research. And if you're even shyer, you can also be a part of a semi-technical research blog. Yeah, we will be publishing it on behalf of you, and you can be a part of that journey as well. So the possibilities are endless. All we want from your side is to step up and show the world the power of your research. So, and yeah, that being said, we are having a webinar session, an exciting webinar session again from next to next Sunday. You can follow all the updates on our Facebook page, www.facebook.com/researcheronweb.com. You can also visit our website and see all what has happened in the past few months, how we have boosted research in www.researcheronweb.com. Yeah, I remember a lot of URLs, and that's my job. So, thank you everyone for being a part of this great, amazing webinar session. Uh, have a great Sunday. Have a great week ahead. Stay safe, take care, and get vaccinated. Thank you. This is Shubhapriya signing out from the Research.